And
Yes.
do you see my screen?
We can, yes.
Okay, perfect. All right, so just I'm just going to give a little bit of an overview, and then Eric is going to take over with some of the implementation details that we've been going through. So essentially, this is coastal ocean modeling work. The models that we're working on are used by FEMA as well as NOAA for forecasting systems and by the Army Corps of Engineers. And by the way, all the people in green are currently working on this particular implementation. So it's a collaboration between Illinois, Notre Dame, UT Austin, and Ohio State. So the kinds of problems that this class of models looks at is predominantly coastal flooding, but also wave forces, inundation of sinking deltas, wetland degradation, fisheries, and even things like oyster and other larval transports. So here we see the general spectral energy content of the ocean. And there's actually quite a bit of energy in this long wave, what are considered long wave zones, and quite a bit of energy in the short wave or wind wave zone. And this is not really resolvable on any kind of large scale. So we tend to use energy transport models versus we use derivatives of Navier-Stokes equations for this range of energy here. So these are really coupled together through two different classes of models. And the one that we're predominantly working on in this project is ADCIRC. And then there's a wave energy model called SWAN. And
we're still on the title slide.
Oh, am I?
The share hasn't moved past the title slide.
Really? Let me try again. That makes it a lot more boring talk. How about now?
That worked.
Okay. I guess it was trickery. I have multiple screens, so I moved it so that it would be a little bit easier to present. So anyway, this is the spectral energy in the ocean that I was talking about. So you have the long wave over in here and the short wave. Are we now on evolution of coastal ocean hydrodynamic models, the recent past?
Yes.
Okay, perfect, thanks. Anyway, so we're coupling two models here. These go back and forth. I'll talk a little bit about that. And they get a one-way connectivity with a global atmospheric model and giving us winds and atmospheric pressure. And ADCIRC in itself uses METIS-based domain decomposition with a halo overlap. We have very large domains with it. And most of the resolution is actually overland. So that's reflected in this static load balanced depiction of the domain decomposition. So these all get assigned to their own core and they communicate at the interfaces. Again, the larger domains here are in open waters. And when you get to the smaller domains, the smaller decompositions, i.e., which balance the number of computational points there, they're overland. And this gives a little bit of a motivation of the work. So the bottom line is a lot of this remains in the classic implementations that we've traditionally done. This remains dry. So obviously rebalancing the load is pretty critical. And that's why we're using AMPI. In of itself, the code is quite scalable. Here you see some different examples on different systems. This is the past, and this is using some of the older systems in terms of scaling. We scale up to about 30,000 cores, and of course it's weak scaling. So the bigger the problem, the better it scales. So this is a typical domain, just to give a little bit of background. This is the US East Coast, Gulf of Mexico coast, Florida, et cetera. And you use a big chunk of ocean like that, but you pile a lot of resolution on in the nearshore areas. So if we were to zoom in on one of those areas of interest, this would be, for example, Mississippi River Delta with New Orleans in the background there. And this is the representation in the unstructured mesh model. So you have enormous detail of the geometric complexity as well as the hydrodynamic features of the model. That's represented, of course, by using very targeted, high resolution and pretty sophisticated meshing methodologies to capture that. A typical simulation goes like this. You have the winds over here, hurricane winds, for example, and this is used predominantly for hurricane modeling and big storm modeling. You have the waves over here up to 10 meters, and then you have the storm surge piling up within the geometrically complex system. And that's how the model is used. Now, moving forward, what's the future and what are we working on just after that background? So what we're going for in our collaboration that we're talking about today is really being able to rebalance the physics as well as being able to rebalance the computational load. And of course, those two are intertwined. Down the road, we want dynamic, and we've been working on this for quite some time, dynamic mesh resolution as well as to choose from a variety of order of interpolants in more advanced finite element implementations, such as discontinuous Galerkin. So we really want to develop these frameworks that allow for dynamic and coupled physics and have the much more sophisticated load balancing as compared to the current implementations of the model. So the multiphysics really comes into coupling not only the long wave circulation model that I talked about before, as well as the waves. This is a little bit different wave model, and have that coupling coupled to the atmospheric model, weather model. But we also want to pull in global ocean circulation models, sea ice models, and hydrology models as the first order, and we've been working quite a bit on this. So just for example, the background ocean climatology, which you see over in here, this is surface water elevations as they would be observed from a satellite, but here computed by ADCIRC. It looks something like this. The reds are higher water levels, and the blues are lower water levels. And there's quite a bit of variability there, 3 meters. So it turns out that, for example, the water along the East Coast is a meter lower than further into the Atlantic due to the current systems and how Coriolis interacts with those. And so a visualization of the East Coast of the United States looks like that. And you can see that higher water pop up, but you can also see the ephemeral nature of the many eddies and complexities in the ocean. So the current system, for example, that we were seeing over there is the Gulf Stream, as well as the loop current. And you have many of these systems around the world. And here it's visualized. And that, of course, impacts water levels as well. So this is bringing in more physics into the system. If you were to look at comparisons to mean water levels averaged over a running 30-day average, you would see that these systems which have the coupling in red match the measured quantities in black much better than the uncoupled systems in blue. So basically the coupling of the physics leads to better results in terms of predictability of the models. The spectral content is also significantly better in this example over here. If we were to look at this picture here, where you have a spectral between the year range and about the 5-minute range, spectral energy density of the system. So now the next step is really to pull in physics into the ADCIRC framework itself, not the coupled models that are running simultaneously, but within the core of ADCIRC. And the main thing that we're working on is to change the hydrologic components that couple in with larger scale hydrology, i.e. the rainfall runoff. And that is with these two sets of equations that are essentially simplifications of the shallow water equations that are typically run much cheaper and much better for the hydrology. So the idea here is that you can pick clusters of elements that run more complex physics a simpler set of physics and an even yet simpler set of physics, and have the boundary of where that physics gets applied change depending on the hydrodynamics. So the simplest example of that would be, for example, here. And you see that there's dry land over in here that's depicted. The light blue are the wet areas, and then the green and white areas are dry areas. And so there's basically no computations in the current implementation being done. So this would beg for, again, rebalancing. And a very simple example is over here, where again, you have a much higher resolution on land than in the ocean. The line being the beach that separates things, and water going up and down, past and forward and backward of that line. So a much better decomposition is this, and then the one to the right, and it needs to be dynamic. And so we have seen with Zoltan improvements in efficiency that way, and we're working now to implement AMPI. So an example of where this is all going is here, and you see the incredible complexity of the very dendritic network of channels, depending how well you resolve them, 30 or 120 meters for NOAA's operational models, really determines how much resolution you have on that coastal floodplain. So this, again, these are dendritic channel systems penetrating the floodplain. And so you have the ocean side, the land side with a lot of nodes, and a lot of those nodes are either going to have hydrology, which is much cheaper to run, applied to them, or are simply dry and don't need anything. So that's what we're working on. And so instead of having this very simplistic one directional flow structure in terms of how things work, we're envisioning a much more interactive system where the physics, the numerics, as well as the how the computational implementation works are interactive. Eric, it's over to you.
Thanks.
And that was, I think, 12 minutes.
All right. Is my screen visible?
Yep.
All right. And we'll change slides. Have we changed slides?
Working.
All right. So this is the AMPI specific side of the talk, presented by myself, Eric Bohm, Senior Research Programmer with the Pilot Programming Lab, doing the work done by myself, Dom, Dylan, Sam, and Justin. So we look at ADCIRC-CG as a software target. It is a Fortran-based MPI code, mature, a lot of features, over 100K lines of code in total, most of those in Fortran. And as an application, as previously described, it essentially has this two forms of cells that we're looking at: the wet cells, which have different kinds of real physics depending on the cell. That's where all the real computation actually happens. And the dry cells, which are just there in bookkeeping mode until they actually become wet enough to have real physics. This creates a dynamic load imbalance that emerges from the simulation and changes over time. And so this is a perfect target for the kind of thing we want to look at with Adaptivempi. And the challenge that we face is in Adaptivempi, I'm not going to, this is just the highest level description of it. It has virtualized the MPI rank so that it runs the user level instead of which also makes assumption.
Eric, you're breaking up, so I think it's
And
internet connection maybe.
Not sure what to do about that. Am I still breaking up?
Okay, now it's better.
Oh, I didn't make any changes. So, but all right. So I deal with the fact change the one process assumption, and this creates a problem with respect to global mutable state, which in many programs there's associated with a rank or at least with a process. And now that we have changed the ranked process model, we also have to deal with the process-based variables now being thread-based variables. And so in many cases, this is handled by a privatization approach where we take what was global state and we localize it to the user level thread. And AMPI has a variety of approaches to this. The one that we looked at as being most appropriate for ADCIRC is the TLS privatization technique, the thread local storage technique. This is supported in Fortran by adding the OpenMP flag. And within Trump plus usable threads, we can also take the translation of a TLS pragma and localize it to the actual user level thread. And that is achieved by adding the TLS globals flag to the AMPI CC compile line. And then adding the exclamation $OMP pragma for thread private for each variable after it's been declared in the Fortran code itself. So per variable, that's fairly straightforward. However, when you look at a mature Fortran code like ADCIRC, there are over 2,000 individual variables. And so that creates an incentive to handle this in some automated way. And as we look at Fortran global state in general, there are some additional complexities that have to be managed. So as noted, the module available variables need to be handled. But if they have the parameter attribute, they are constants and must not be handled with TLS. Similarly, in a subroutine with a save attribute, those become global and need TLS. In a subroutine with initial value are implicitly saved and need to be handled with TLS. But variables declared a subroutine otherwise are local and should not be given the TLS pragma. Likewise, the old classic common blocks promote variables that they list to become global. And so the common block itself needs to be declared TLS, but the variables within the common block do not. And so, although this is a slightly long list of things to keep track of, they actually represent a fairly straightforward set of rules to apply. And so it is something that we can definitely organize as a process for transformation. Similarly, for Fortran IO, this uses something called the logical unit number, and a LUN is referenced in every IO statement. For the people from the C and C++ side, this is equivalent to a stream or a file identifier. However, it is part of the global state and part of the Fortran runtime. And therefore, in order to manage this sort of safety issue that we have with mutable state, we have to manage these LUNs. And so we have to transform each of these when they are actually file operations. And here, Fortran throws us a little bit of a curve because all of these things that are written as file operations can also be used to apply to strings. And so these transformations must only be applied contextually based on whether or not the LUN in question is operating on an integer and therefore a file IO-based operation, or not an integer, in which case it is essentially a string operation and local to the string address space, and therefore does not require any transformation. So again, a set of rules that we can automate. So we wanted to figure out the best way to do this and looked around at a bunch of projects that might help us to do this. At the time that we initiated this, early this year, flying was not at a state where it could do that. And our most recent examination, it's still not quite there, but we are hopeful that it will get there soon. So we decided to move forward with a proof of concept implementation, just setting up a script to parse the Fortran source code directly using regular expressions, apply the rules that we previously described for variable declaration and IO statements so that we prioritize where necessary and integrate a application level module called CK-LUN, where we simply arithmetically add a rank-based CK-LUN variable to each integer LUN so that it becomes, in fact, safe to operate on in a thread level way. This creates an additional challenge in that when we actually migrate a rank, we have to close any of the open LUNs and reopen them after we've completed migration. And the implementation of that was accomplished by Dom, one of our collaborators from Notre. And that process involved implementing the about to migrate callback, and where he just records the open file in its current LUN data state, and then close, and implementing the just migrated callback, where you reopen each of those files and restore the previous LUN state. And we have to register those callbacks with AMPI with these two calls so that when a virtual rank is migrated, it automatically triggers the appropriate callback and migration can be handled robustly. So current status is that we can run AMPI with ADCIRC, well, compile ADCIRC onto AMPI and launch it in both using SMP or non-SMP versions of Charm. We had an initial issue where there was a bug in MPI weight sum that was found and fixed. So we were able to move past that. And we are currently, as we are still only in the very first year of this project, in the finding the problems phase, not the producing results phase. But we are moving fairly well along in tracking down instability in these long runs and coming up with a way to manage support for the net CDF input form. And our experiments so far have found that the virtualization approach has been negatively impacting performance. Our detailed analysis shows that it is a performance problem related to MPI all reduce being done on the subcommunicators that are used in ADCIRC for the ranks that are not IO ranks. And Sam is working on a solution to that. So future work is that we are going to implement the transforms that we have manually scripted in Flang or Flang as augmented by supplements that may be necessary, so that this kind of approach can be applied to other projects more easily and to avoid having a sort of cumbersome alternate version of the code. We're going to integrate meta balancer use so that we only trigger balancing after a sufficient amount of imbalance has been automatically found. The aforementioned improvements to AMPI's subcommunicator collective performance and integrating application specific balancing hints. And some of these have already been designed and in process in the work that was based on using Zoltan as a balancer, as there are some fairly straightforward applications of simply looking at the elevation to help fine tune when one is going to open a list of dry cells to see if they have become wet, and that way you can avoid a fair amount of overhead by not exploring things that have no chance of needing the actual hydrology physics. Furthermore, we're going to be exploring graph-based partitioning due to the connected nature of the operations along the mesh. And with that, I'll open the floor to any questions.
All right, thank you for the presentation. I think we have two questions on the Google Doc. The first one by Phil, it's probably for Joannes. What's the distance between those low valleys and high ridges of sea level of the US East Coast?
What's the difference between what?
What's the distance between those low valleys and high ridges of sea level?
You know, that's, I would guess it probably extends out maybe about 100 or so kilometers. So,
Okay.
100 to 200, depending on where you're at.
I guess just looking at the picture you showed, I was curious about, effectively like a slope on the ocean surface. But at that distance, it seems like it'd be pretty unnoticeable.
Oh yeah, you wouldn't notice it.
Thanks.
Yep.
And the other question I had, I guess directed to Eric or the other folks on the project is, was there any consideration using ROSE for the Fortran transformation, since there was existing code to do some of the AMPI privatization for both C and Fortran using a ROSE-based tool way back
We
when.
we did give it some thought, but the current status of ROSE and future of ROSE was somewhat foggy. And I think Sam's experience with ROSE didn't leave us enthused about trying it again.
Yeah, I won't necessarily disagree with that decision. Even having worked on that code. Thanks.
In the XPEC Center, we had issues with ROSE being able to parse their main Fortran code. And I'm not sure what the status of that is, of ROSE is now as a project.
I think Dan was the only one working on the Fortran aspects. The rest of the team was not. And I think if I'm not mistaken, that project's funding got reduced, so the number of staff is probably small now anyways. But the Fortran, and then now I think we have this new hope on the horizon in the form of LLVM Flang project. And so we are hopeful of that and the lib tooling to do more things automatically. And yeah, I guess that's enough on that. And I think you will hear more about AMPI in the next talk. I suppose we should reserve some of this for that. But I was tempted to say more, but I guess we should do it in the next talk.
Are there any other questions? I think Francois had a question here in the chat. About the images Joannes showed, what sets the spatial distribution of the grid nodes?
Oh, so we go anywhere from about, in the operational meshes, from 30 meters, and then they extend out in the deep ocean to about 12.5 kilometers. And then the global meshes go as large as about 24 kilometers. So we're somewhere between 30 meters and 24 kilometers. And in the global operational models that we're building for NOAA, they cover all the world oceans, including the entire Arctic Ocean.
I was wondering about the sort of the refinement. Is that it looked continuous, I guess.
Oh yeah,
what sets that?
So that is done on a lot of functionality that we have pulled out of graphics type of algorithms. So for example, there's medial axes that are computed. There's rates of change of directionality of the boundaries. There's bathymetric depth functions. There are topographic gradient functions. So, and then we put it into a framework that essentially controls the variability, or how fast an element can grow or shrink. And that actually is important because you degrade the formal order of accuracy of the algorithms, obviously. And so we set very high controls of that. And because of that complex nature of the channel systems on the floodplain, you get enormous numbers of nodes on the floodplain. And then there's also geometric and topographic complexity on the floodplain. So the ultimate idea is that the ocean is still a simpler place than the floodplain. So right now, whereas the meshes I was showing you are balanced 50-50 between ocean waters, even covering the globe, and land waters, which can extend to, for example, all US coastal floodplains. In the future, we would probably have 90% of the meshes on the coastal floodplain and 10% of the mesh in the ocean. So there's an enormous lob of nodes in the floodplain that, unless it's raining or flooding, are never being used. So that's the whole idea of the load rebalance.
That's fascinating. Thank you.